Here's the ultimate paradox of spaceflight. Launching a rocket straight up, perpendicular to the plane of the planets, takes more energy than flinging it past Pluto. Not a little more, a lot more. It's the most brutal fact in orbital mechanics, and it's the one your gut refuses to accept the hardest. You know the neighborhood, right? Earth, Mars, Jupiter, Saturn, Neptune. The planets all move on pretty much the same plane, like marbles rolling around on a tabletop. Asteroids on the plane. Well-behaved comets on the plane. And every single probe we've ever launched, Voyager, New Horizons, the Mars rovers, all of it is born inside that disk and stays inside that disk. We call that plane the ecliptic, and it's the chessboard we've been playing on since day one. There are two ways of moving we've gotten really good at: forward and sideways, staying in the disk. And there is a third direction: perpendicular, straight up and straight down, above the plane and below it. That one we've basically never taken, and the reason isn't distance. It's something way sneakier. And the best way to get it is to set the entire solar system down on a turntable. Seriously, picture it. A vinyl record spinning. The sun is the label in the middle. The planets ride in the grooves. And the whole thing has been turning without stopping for 4.5 billion years. Now, drop a gnat onto that spinning record. At some point, the gnat decides to leave, and not by walking to the edge. No, it wants to lift straight off, straight up toward the ceiling. Easiest thing in the world, right? Just open your wings. Except anybody watching from outside will never see it go straight up. They'll see it go flying off sideways, slung outward along a path it never chose. Sure, it gains a little altitude, whatever its wings can claw out of the air, but in that exact same moment, the vinyl underneath its feet has already hurled it away, and it's not even close. Here's the merciless part. The second it lifts off, the gnat takes the record's full speed with it. It thinks it's flying up. What it's actually doing is shooting off on a tangent. To really go up, to hover right over that label in the middle, it would first have to pull off something colossal, cancel out all the speed it inherited without ever asking for it. Kill the merry-go-round first, then climb, and that's where it would run into the trap. Breaking that spin costs enormously more energy than flapping your wings. The problem was never the altitude. The problem is inertia. And yeah, that gnat nailed to a path it never picked, that's us. Because Earth is screaming around the sun at 67,000 miles an hour. You can't feel it, but it's happening right now while you're watching this. And every rocket that leaves this planet gets handed that speed for free, which is an incredible gift, as long as you want to move around inside the disk. To get to Mars, you just tweak your heading, and the speed you already has does almost all the work for you. Quick thing before we go any further. If this is your kind of rabbit hole, the one where the obvious answer turns out to be the wrong one, subscribe and tap the bell, and the next one will find you on its own. But try pointing straight up, really up, perpendicular to everything, and that gift turns into a ball and chain. First, you have to zero out your own 67,000 miles per hour. Then, and only then, you can start climbing. Engineers call the speed a spacecraft has to produce on its own delta V. Getting to Mars takes maybe 2.5 miles per second. Getting out of the plane vertically takes something like 26. More than 10 times as much, all in one shot. That's why nobody goes. The disk isn't just our house. It's our cage, and we've been wearing the bars since birth. Which lands us right back on the paradox we started with, except now you can actually measure it. We've pushed the Voyagers more than 15 billion miles out into the space between stars. The farthest thing we could possibly reach, we reached. But straight up, over the solar system's head, looking down on the whole thing, almost nobody has ever been. The most distant place, yes. The closest one, no. And now we get to the part almost nobody talks about, which is honestly my favorite. Because right now you've got a nice, tidy picture in your head, don't you? Flat disk, sun in the middle, two clean arrows pointing up and down, north and south of the solar system. Throw it out, the whole thing's a lie. Start with that up. Where do you figure it points? Toward the top of the galaxy, right? Nope. Our disk is tilted about 60 degrees relative to the plane of the Milky Way. 60 degrees. We're crooked. Stand on the North Pole of the solar system, fly straight up, and you're not heading for the galaxy's up. You're wandering off on your own toward the constellation Draco, the Dragon. Go the other way and you pop out in the southern sky over near Dorado. The solar system's up and down have absolutely nothing to do with the Milky Way's up and down. We're a disk lying crooked on the table. And that disk doesn't sit still for a second. While it spins, the whole solar system is traveling. We're running toward the constellation Hercules over by Vega at roughly 45,000 miles an hour relative to the stars around us. And the entire neighborhood together is tearing around the center of the galaxy at more than 500,000 miles an hour. One lap takes 230 million years, what's called a galactic year. Last time the solar system was sitting exactly where it is now on that orbit, the first dinosaurs were just showing up on Earth. And it doesn't even stop there, because as we circle the galaxy, we also bob up and down through its plane, like a carousel horse going up and down. So yeah, we've got too many ups and downs, and not a single one of them lines up with the others. Then there's the wind, because out there between the stars, it's not a perfect vacuum. There's thin gas, and we're plowing through it. From where we're sitting, it's like sticking your hand out the car window on the highway. We feel an interstellar wind blowing against us, and it comes from one very specific direction, roughly over by Scorpius. That wind is what shapes the front of our bubble, the nose of the solar system. Put it all together, and the mental picture flips completely. We're not a motionless disk with a clean up and down. We're a crooked, spinning top, flying sideways toward Hercules, wheeling around the galaxy, bobbing above and below its plane, and taking a headwind the whole time. And up and down aren't even symmetrical. On one side, you're staring the wind in the face. On the other, you're in the wake. That neat little diagram from your school textbook? Very politely, it's a convenient lie. Which makes the real question hit even harder. What is up there and down there? What would we actually gain by getting off the disk? A lot, and it starts with dust. Because our disk is dirty, it's not just planets and vacuum, it's full of an incredibly fine haze, the crumbs of billions of years of comets shedding and asteroids rear-ending each other. And you can see that dust with your own eyes. On a really dark night, just after sunset, that faint pyramid of light rising off the horizon, the zodiacal light, is sunlight bouncing off it. That's the inside of our disk, lit up from within. A probe that climbs above the plane leaves that haze under its feet within a few months, and up there the view gets stupidly clean. No more glare from dust, no more background veil. It is literally the best place to put a telescope in the entire solar system. And that's no small thing, because that haze is enemy number one for the instruments hunting habitable planets around other stars. Get it out of the way, and suddenly you can see things that, from down here, are just lost in the glow. Signs of life somewhere else, maybe. Or the very first light of the universe. Stuff that from in here, buried in dust, always stays a little blurry. Then there's the shape of our own house, and this one's even more embarrassing. The sun wraps us in a giant bubble, the heliosphere inflated by its wind. It's the bumper that shields us from the nastiest radiation in the galaxy, and how well it protects us depends on what shape it is. And we don't actually know what shape it is, because we've never seen it from outside. For decades, we pictured it like a comet with a nice long tail streaming behind. Then in 2020, a team led by Mirav Ofer at Boston University ran the numbers again and got something very different. More like a deflated croissant. 2 curved lobes, no tail at all. So who's right? Nobody knows. The 2 Voyagers did punch through that boundary for real, but at 2 points from more or less the same side. That's like trying to guess the shape of a balloon by poking it with 2 fingers. To actually nail it down, you'd have to climb up high and look down. Which brings us to the thing that, for my money, is the wildest of all. We've taken photos by the truckload. Earth from orbit, Saturn backlit, Pluto's frozen surface. But a photo of the entire solar system shot from above, face on, like a disk seen from outside, doesn't exist. Never taken it. Yes, 40 years ago, Voyager 1 turned around for that famous family portrait, but from barely 30 degrees above the plane, with the planets reduced to smeared dots strung out in a line. That's not a disk seen face on. That's a snapshot from the side. A real look from overhead, our whole neighborhood laid out like a coin on a table, we still don't have. From up there, you'd seen them all in a ring, the planets sitting like the hands of some cosmic clock around the sun, the entire machinery of the system in a single glance. We've been looking down at Earth from orbit for 60 years, and we don't have one single picture of ourselves from that same angle. So, let's go up there, you say. Easier said than done. A bigger rocket won't cut it because the energy to erase that sideways speed is enormous and you could never carry the fuel. So the route engineers are studying is, once again, beautifully backwards. To go up, you first have to dive down. You drop the probe toward the sun, let it fall until at closest approach it's screaming along at hundreds of miles per second, and right there, only there, you light the engines. Burning at that insane speed, deep in the sun's gravity well, gives you way more energy than the exact same fuel burned anywhere else. It's a principle Herman Oberth wrote down almost a century ago. The fall becomes the launch pad. Add a solar sail, a giant sheet pushed by nothing but the pressure of sunlight, and you can slowly tilt the orbit until it's nearly vertical. It takes years to spiral up there, but it burns zero propellant, and the longer it pushes, the higher it takes you. On paper, we've got plans like this by the bucket load. The Solar Polar Imager, plus a long trail of ambitiously named proposals that come back around to the agency's desks every few years. Great ideas, doable, and almost always, when the bill comes, postponed. Too slow, too expensive. We'll get to it next time. The view from above has been the mission of the future for 50 years. Always, stubbornly, the future. And yet, once, for 35 years, exactly once in all of history, something actually made it off the disk. Its name was Ulysses, and it launched in 1990. To pull off the impossible, it had to take an absolutely insane detour. It flew all the way out to Jupiter and used the giant's gravity as a slingshot, bending its own path almost 80 degrees. It basically stood itself upright, the only thing ever built by human hands that has climbed that far above and below the plane of the planets. For years, it ran up and down through the disk, feeling out what space is like up there where nobody had ever been. The fast wind erupting from the polar regions, the dust drifting in from outside, the magnetic field seen from an angle nobody had ever had. It worked until 2009. And it never took a single photograph, because Ulysses didn't carry one single camera capable of imaging what was around it. Zero. It got to the hardest place to reach in the entire neighborhood, that above and below we've been chasing this whole video, and it got there blind. Touching everything, seeing nothing. It could never turn around and look down at the disk and finally hand us that family portrait we're still missing. And now the part that really stings. Ulysses was originally supposed to be a double mission. 2 spacecraft, one European and one American, sent to explore the top and the bottom at the same time. Guess which one was carrying the cameras? The eyes. The American one, which got canceled in the early 80s to save money. Only the European half survived, the one built to feel, not to see. That's exactly how it went down. The one time we got off the disk, we went blind because the spacecraft with the eyes got sacrificed to a budget. And then, 35 years later, we went back, and this time, finally, we packed the cameras. February 2025, a European probe called Solar Orbiter tilts its orbit out of the plane. No Jupiter this time, no grand detour to the outer system. Venus over and over, 5 separate flybys since 2020, each one nudging the orbit a little further off the ecliptic. Slower than a slingshot, also a great deal cheaper. And on March 23, 2025, from 17 degrees below the sun's equator, it looked down and photographed the sun's south pole. First time in history. Think about what that sentence actually means. Every image of our star ever taken before that, every single one, from Galileo's sketches to the telescope in your neighbor's backyard, was shot from within a few degrees of the same flat plane. Because that's where Earth is. That's where we all live. Ulysses had been up there 35 years earlier and could only feel it. Solar Orbiter finally saw it. Now, before you get excited, and this is the honest part, the pictures are not beautiful. From that distance, with instruments that small, what came back is grainy and low resolution. Nothing like the sun you're used to seeing in the news. Anyone hoping for a revelation got a smudge, but that was never the point. For the first time, somebody was standing somewhere else, and they had eyes. And it isn't finished climbing. This coming December, it swings past Venus again, and the tilt goes to 24 degrees. By the summer of 2029, 33. Every pass, the view over the pole gets a little better. And yet, look at what Solar Orbiter is pointed at, the sun. It's staring inward at our star from above, which is the picture we were missing of the sun, and now we have it. It has never turned around. We've got the numbers from up there, the wind, the magnetism. We've got the poles of our own star, blurry, but ours. The image? No. The whole disk seen from above, us looking at ourselves from outside, we still don't have it. It's the one direction we never took seriously, and it is the one photograph that's still missing. And here's the part that should bother you. It isn't hard anymore, not the way it used to be. Solar Orbiter just proved the climb is affordable. Nobody has simply decided that the view is worth pointing the camera at. So what are you taking away from all this? Does it get you more that going up costs more than reaching Pluto, or that the one time we went, we left the cameras at home? Go wild in the comments. And if you want to see the other side of this problem, somebody has worked out how to get roughly the delta V we just called impossible out of 3.5 pounds of carbon film. No engine, no fuel at all. Watch, we can reach another star without fuel. It's on screen right now.